All right. Hi, my name is Jenny Thomas, and I teach 8th grade currently in Sacramento, California. And as far as my classroom is concerned, I have levels from special ed students all the way up through GATE students or honor students. And this is just some of the things that I've developed, a quick sequence of lessons focused within the realm of nanoscience. And quick shout out to Stanford University and Daniela. I attended their teacher education program in 2019. And so this is an ongoing classroom development from that beginning. So nanoscience, a teaching adventure. Okay, so nano being within the realm of things that are very, very small, between microscopic and atomic, and figuring out a way to help the kids understand something that they can't see. That's one of the big challenges in teaching middle school is we can't see it. So how can we understand it? How can we do some activities where we have an opportunity to experience something, observe something, and then start to understand something that's absolutely abstract? So in what I teach at the 8th grade level, I usually involve nanoscience in a standalone unit toward the beginning of the school year after teaching a little bit about matter, particle model of matter, a little bit about energy. So we touch on light, the electromagnetic spectrum, and then we get into nanoscience, and we use those ideas as a foundation for the other units and the other topics we dive into, because nano, as you know, pretty much undergirds every aspect of the world around us. So a prerequisite to the lessons I'm about to share right now is that, first of all, what is light? It's this form of energy, and we talk about the electromagnetic spectrum. Well, what is white light? It's the visible spectrum of all colors of the rainbow. What causes a rainbow in the sky? Where do these colors come from? And by the way, why are things the color that they are? For example, something like a red apple. What gives it its color? So we can look at it from the standpoint of color can be produced in two ways. And when we talk about light energy, we're talking about pigmentation of objects and how they get their color. But as we dive into nanoscience, then we get into something that's a little different, structural coloration. So the visible spectrum is part of the electromagnetic spectrum, and visible light falls within the nanoscale. 400 nanometers to 700 nanometers approximately. And again, this is all prerequisite. What is the only thing our eyes can see? Light. Well, if white light is shining down on everything that's in the classroom, why are the chairs blue? Why is this apple red? Where does all these colors come from? I don't see colors or rainbows shining down on us. And that gets us back to what is white light made of? And so we make spectroscopes so the kids can actually see, there are the colors. They're within the white light. That all colors of the rainbow combined make up our white light. So in the first lab, we do an observation of thin films. And so we look at questions like, well, okay, what is the color of water? Oh, it doesn't have a color? What about nail polish? If I give you some clear nail polish, what is the color of the nail polish? That doesn't have any color either. So then we do the lab and we make an observation. And when we make that observation, we end up seeing some colors. Where do those colors come from? Is it from pigment like the apple or the chair in the classroom? And if not, how can we explain that? So does size really matter? Looking at thin films. So the materials we're using are water, some kind of container, clear nail polish, some metallic Sharpies, some black construction paper. Uh-oh. Yikes. Oh no, I hit a glitch.
I'm ready. Oh, there it goes. Okay.
Oh, sorry about that. My video didn't play. I have a video. Nope. Okay. I guess we're not seeing videos.
That's okay, Jenny. This just reminds us all of why we're so glad to not be virtually teaching and being in the classroom with our students. So no worries.
Yes.
Oh, goodness. Okay. Sorry about that. I had some videos of my kids actually doing the experiment. Okay, so when you dip the nail polish in the water, it spreads out and polymerizes, forming a thin film on the water. So we get a chance to see those rainbow colors. And again, thinking about, well, there's no color of water, there's no color of clear nail polish. So where are those colors coming from? So thinking about what's happening with those light rays as they hit that thin film. So the nail polish spreads out into a super thin film, which creates that iridescence, that rainbow color. Hey, there's some pictures of my kids actually doing the experiment. So I just give them little plastic lunch trays. We put water in there. They take the black construction paper, they dip it under the water, and then drip a little bit of nail polish on it, and then lift up that construction paper. Okay, so then there's a sequel to this. Okay, so we got to see that somehow there's color on that film of clear nail polish. All right, well, what about soap bubbles? So we do a little bit of investigation with soap bubbles. So instead of that thin layer of a thin film, which is more two-dimensional, we get to look at a three-dimensional sphere in the terms of a soap bubble. So do we see any colors in our bubbles? Are those colors due to pigment like they were with our chair and our apple? Or is it more like what we saw with the thin film? What determines the color of a bubble? And we can actually, I've got some videos and some links in the links that will be shared with you later, as far as some great videos that dive into this topic a little bit, as far as, well, how come there are colors, but not only that, why are the colors changing? What makes those changing colors or those swirling colors? Okay, so again, we have our container, we've got some soap bubble solution, and we're going to make something called a flim flam. And this flim flam is basically just a couple of plastic straws with some string or yarn looped through it so that we can have a frame in which to have a film of soap and be able to make some soap bubbles. So there's some of my kiddos, and they're blowing on that. So they've got this soap film between the straws. And if you blow on it, you can make some pretty big bubbles, which gets a little crazy messy, but it's one of the labs they really enjoy. So dipping your flim flam into the soap solution, holding it up, holding it horizontally compared to holding it vertically. And what kind of films do you see? And how do those colors change? All right. And again, apologies for not letting me play my videos. So here's some pictures of my kids holding it. And you can see the different iridescent colors there. And they'll notice not only that there's iridescent colors, but the swirling of the colors. And as they tilt it and change it, you see changes in those colors. Okay. Again, some of the thin films. So when looking at the bubbles, similar to oil on water, we see these swirling of colors. And these colors are visible because the film is thick enough to reflect the visible light. And again, like I say, it gets a little messy with the soap, but being able to look at the bubbles, see the colors in the bubbles, and then try to explain what's going on there. Hey, what colors do you see the most? Which color is most common? And they can actually take a plastic ruler, and if they dip it in the soap solution, they can slide that ruler through the bubble and measure the size of the bubble and get some dimensions there. And again, be thinking about, well, does the size make a difference, or what's going on as far as these swirling patterns in these colors that we're seeing? Okay, so looking at that interaction of light with the soap bubble. And then talking about, well, is there any correlation between the color that we see and the thickness of the bubble? Can we actually figure out the thickness of a bubble at a certain point based upon the colors that we're seeing there? So we'll draw the soap bubble, we'll color the soap bubble, and we'll label the soap bubble. How many nanometers thick is the solution in this particular spot when we're observing that particular color? Okay, and so then again, thinking about those films being only a few hundred nanometers thick, and that the thickness correlates with the colors that we're actually seeing. What's going on? You can get into constructive interference and destructive interference as far as which colors or which wavelengths of the visible spectrum are reflecting, which are being absorbed. How are they bouncing off? How are they being magnified? And that gets us into structural coloration. And we can tie that in with things that we see in nature, things like the morpho butterfly. So what makes the morpho butterfly have its color? And how is that different than when we talked about the apple or the colors of the chairs in the classroom, for instance? Hey, there's some really great videos on TED Ed. For instance, what is the rarest color in nature, which dives into this a little bit. And the video is great because it talks about, well, okay, so blue pigment is very rare in nature, but structural coloration allowing us to see blue is actually not very rare. For example, the sky, when we look up to the sky, what's happening with the light? However, red pigment is very common, but structural red pigment or red color is very rare. Okay, and then there's also another great TED Ed video about microraptors. In other words, taking a look at fossils and being able to determine the actual color of something that no longer exists, something that's extinct, based upon the spacing and the structure at the nanoscale, which is pretty cool. We can also tie this in with liquid crystals. So if the color correlates with the thickness of the soap bubble in certain portions of that soap bubble, then, well, what's going on with liquid crystals? We could tie in with nature liquid crystals, things like chameleons, for instance, and how they can actually change the dimensions of different portions of their body and change the color that is showing. In other words, spreading those structures out or bringing those structures closer together, which again ties in with our morpho butterfly as well. How are the spaces for those nanostructures correlating with the wavelengths of light that we're actually seeing? Then we could tie that in also, okay, so size does matter, and there's an interaction between structural size and thickness with light, but well, what about thin films with regard to some other properties of matter? What about something like magic sand? So not necessarily how it affects light or light interactions, but hydrophobic, hydrophilic interactions. Okay, so here would be a setup of the lab. And again, I apologize for the videos not playing, but the kids taking and adding water to regular sand, comparing that to what happens with so-called magic sand, which has a thin film of material on it that makes it hydrophobic in the presence of water, the opposite of hydrophilic, natural sand. And then of course, well, what happens if we take that one step further? We take the magic sand, put it in water, but then we add something like oil or surfactant. How does that change the interaction that's occurring? So there's my kiddos there, observing the differences. And again, reading some articles, and I have some articles that are in the materials that I'm providing with this presentation, learning about, well, what's causing that? Why is this sand different? Other than the fact that it's, pigmented blue, what is different about it that it interacts with water in a different way? What are some connections? Well, we can take a look at things like lotus leaves and paint that has been developed to have that hydrophobic property. We can look at things like pitcher plants, which have hydrophilic properties to be able to cause insects to fall inside so they can eat them. Things like soap. And there's actually kind of a connection there with cell membranes as well. And overall, you could actually use soap bubbles as an anchoring phenomenon in investigating nanoscience. So soap bubbles are a thin film, they're three-dimensional. We can look at the light wave interactions and from there connect to structural coloration and things like a morpho butterfly. And we can look at the change in thickness correlating with a change in color. And that can tie in again with liquid crystals and things like chameleons. There are other type of thin films, magic sand, things that are hydrophobic or hydrophilic based upon the application of that thin film. There are other connections with soap bubbles that I didn't get into, things like surface tension, forces and energy conservation, the shape of it, a sphere. Why do bubbles want to be spherical? Surface area, the idea that a bubble may bounce on carpet, whereas if it touches your finger, not so much. That there's also an element of self-assembly. And that ties in with lipid bilayers and even a cell connection. And I think that pretty much sums it up.
Danny, I would like to say how very impressed I am as a high school teacher to see these things that you're doing with your middle school students, and truly high quality. When your first slide showed phenomenon, right? Anchoring phenomenon. That is exactly the way that we are now learning is the best way in with students to engage their curiosity and their interest, and with something like a bubble that they have been exposed to their entire lives and never really had anybody to explain it, help them understand it. So absolutely love that you are just phenomena first in these investigations. Thank you so much.
Yeah, thank you for the feedback. Appreciate that.
And making a mess is always fun.
Very true. Are there any questions or other comments? Well, we can go back to questions and comments at the end. Let's round of virtual applause to Jenny, and let's give the floor to Suzanne. Suzanne, I'm ready to share your slides.
Okay, go ahead.
And Maria, just to let you know, there are comments in the chat. So Jenny, if you want to check this out, there's a question.
Well, while I pull it up, let's just read it. Have you aligned state standards with this lesson?
Yes, absolutely. In the state of California, we adopted next generation science standards. And so the idea of moving from phenomena, investigating phenomena, and then asking questions about those phenomena, and then being able to take something that is, again, abstract and not visible. What can we visibly see? We can see soap bubbles, we can see sand, we can see a film on black paper. And based upon those observations, start to think about what's happening at an invisible level. So specifically for my grade level, we're supposed to teach about light and light interactions. And that's one of the big things, as well as just, how does matter interactions with matter. So hopefully that's a sufficient enough answer.
And I'd just like to add on, just to give some context for those teachers that are maybe new to teaching nanoscience. Jenny is a rock star and has been learned about nano since 2019 and really just jumped full in. So just keep in mind that you can start with one small lesson, and as you get a feel for it, you can continue to build. So please keep that in mind. I know as from being a teacher and being in that position of what it's like to put in new curriculum. So think about it as just one step at a time.
Very well said. Suzanne, the floor is yours.
Yes, and you could go ahead to the next slide if you would, please. And I want to repeat what others have said, that like Jenny, you're the first person that made me want to go back to 8th grade in ever, including when I was in 8th grade. And also what Daniela said, I think it's really important, like how I integrated it is more in a few activities. And I think oftentimes, we are always differentiating for our students and where they are developmentally and academically and everything. And so we have to also do that for ourselves. So like how you integrate it might start with a small activity instead, like whatever you can do in your curriculum, in your classroom, don't be too hard on yourself. If you might be like Jenny and like MVP at, or you might be like me and be on the farm team and just be doing like a couple small activities. So I think we all need to keep that in mind. I'm going to just mention a few things about where am I. So I teach for Blacksburg High School in Montgomery County Public Schools. So this is a very rural district with a large research university in it. So when you think town and gown, that's really what Blacksburg High School is like. So we've got the trailer parks and we've got the university community in a beautiful rural area. Lately, we have had more immigration that was not related to the university, and you can tell that in our community because the food trucks have gotten so much better. So, it's really a beautiful spot, and you can see what I teach here. And these activities I have done in all 3 of these levels, and we are bound by some pretty, I say rigorous, not in the sense of like higher order thinking skills that they are better than any other state, but we do have a state test for chemistry 1. It's being phased out. So I was kind of bound by that at the time that I was integrating these, in that I didn't feel like I could spend too much class time like doing something that would never show up on the test. And, you know, you make the best decision you can at the time you can. So I have a few activities that I've done, and I've done these from the smallest, easiest activity to integrate to the like most intense for me. So next slide. Okay, so this first one is something that really doesn't use any chemicals, but it's rather a modeling activity. I know many of us who teach chemistry, you might have done like act like each of you are gas particles, and how would you react if you were each gas particles, and then what happens if the container volume decreases, and what happens if the temperature increases. So this is kind of a similar thing for self-assembly, where the students are actually self-assembling themselves according to a set of rules or different sets of rules. And the protocol, and this is from Nano Days, and I think I have the original handout either referenced or in the folder that I shared with Maria. So the protocol actually has some very useful connections to nanotechnology. So you can say to students as you're integrating it, you know, this is how this works, and this is this application, and so forth. What we found since the pandemic, you know, a lot of my students now do not want to hold hands like that. Like, I understand it, and maybe there were barriers to that before. So when I would do activities like that before the pandemic, and people were kind of like, in other contexts, like, oh, I don't want to hold a person's hand, I would kind of encourage them to do a fireman grip, maybe, because that is less, seems more approachable for students. But now, you know, lately I've been doing like popsicle sticks or something, and then having them do them on the tables. And that has worked out well also. So the self-assembly is really nice because you can do it with like a lower level, or like less earlier on, or maybe struggling more with science, and keep it simple. And then in my AP class, we talk about how that is a decrease in entropy in that system. And so like, what must be happening in the surroundings in order for that to occur? And we can make those connections to those biological systems as well. So that's probably that type of activity. I'm certainly not telling anybody what they should or shouldn't implement, but that type of activity, if you're feeling like not ready for something else, this is a really simple place to start. It's really easy. There's no setup, you know, and the kids will get something out of it because they'll either be moving around or they'll be moving something around on your tables. Next slide. So when I say start with this, that's just like, you could start with this. It would be really easy. It's not a imperative. Okay, the next thing that I've integrated, and again, this is both at the Chem 1 level, and then sometimes I will just do it for a little fun thing at the AP level, is something on nanoparticles and sunscreen. So using that sunprint paper and seeing, and I don't have any pictures, sorry about that, but you know, seeing how effective sunscreens are. I really like doing this because I know it seems really simple, but that it has connections to their health, you know, in terms of like, wear sunscreen, like Kurt Vonnegut said in his graduation thing, wear sunscreen. So I like doing something like that, that has connections and a reminder of taking care of themselves as they age. And then we can also talk about, you know, the effect of losing the ozone layer and things like that, and the importance of protecting ourselves and taking care of our world. So this is also fairly simple to do, and there's an application that you can be using a spectrophotometer. I don't really do that, but that is certainly something you can do if you want to integrate it. So that is something I think that you could also implement in kind of an ecology type class or some other elective, maybe anatomy and physiology, you know, like a biological type elective if you wanted. So that would be, for me, that would be the next easiest thing to integrate. And I would say that when I've put this into my curriculum, I have just used the protocol that I have right there. Like, I didn't really adapt it. I just used what was there. And that is another piece of advice I have for overworked teachers, is that, you know, it's okay if you don't have time to like rework something and make all your own new slides and all of that kind of mess. Like, it's okay to use a worksheet that somebody gave to you, or buy something off of Teachers Pay Teachers and use it if that's what you've got time to do. So for what it's worth. Next slide. Back up one, I think. Or wait, I can't remember. Okay. Okay, sorry, I forgot what order they were in. Okay, forward one, sorry about that. So this is one that is available from Flynn Scientific, the gold colloidal one. There is a protocol there. And then also I got this as part of the freebies from Thank You Virginia Tech, which did such wonderful nano workshops. And so they actually gave us some free equipment. I think maybe you need to like back up one slide. I'm so sorry, Maria. Yes, yes, stay there. Okay. So we had, of course, that gold material is very expensive, but this is a way, pointing back to what Jenny talked about so well, that the properties of the surface often are much different from the properties of the bulk. And if anybody has done like a lycopodium demonstration where you're increasing surface area, or even just like a kinetics thing where you take like Alka-Seltzer tablets and crush them up and see how much faster they react, then that is
Yeah, I'm hearing you. So
okay. Are we back?
hold on.
I think it's because
All right.
Pam is
We're just gonna mute. Maria, can you mute anybody that's
Yeah.
not?
I think
Taylor?
it's Susanna's double. Okay, try again.
How am I now?
I think it's good. Yeah.
Good now? Okay,
Yes.
sorry about that. I don't know what happened, but okay. So in this, I did want to point this out, that this is one of the biggest benefits of going to these workshops, apart from like the giveaways, which are amazing. Thank you, Tanya. But also just the interaction with other teachers. If you teach in a rural district like I do, there's not like a huge pool of people that you interact with all the time. So it's really nice to go to the workshops and also listen to some of the leaders in their fields. You know, all of us who have been teaching for a while, we are in the classroom so many hours out of the day. It really did make a big difference to me to hear like what is going on now, you know, what are they doing now, and what are the different approaches. And I will say I have a master's degree in chemistry, but that was like 100 years ago. And it was really exciting to me to see all the different pathways that people are going into science from, and what scientists look like today as compared to when I was in college. So that was a really positive aspect of going to a workshop. So I would encourage anybody who has the opportunity to do something like that to do that, if for no other reason than you know, you're going to learn more about like what science is now, and hopefully you'll get some great freebies like they do in our area. So that was wonderful. And also you'll just get some more connections with people that when you have a question, you can reach out and ask, you know. So that is one of the biggest intangible things, I think, and especially for those of us who are in more rural districts, that's like really, really helpful, or it was helpful for me. So anyway, in here, we also have some connections to redox reactions, which is something that I touch on in Chem 1, and then also, of course, in AP. But I think the biggest part of nanotechnology that I emphasize in chemistry is that in general, when you have surface properties and you can increase those surface properties, that can really change the chemistry of whatever it is that you're using. Okay, so, you know, the chemistry at the surface is not always going to be the same as the chemistry in the bulk portion. And next slide. And then this is the last one, and this is one that I actually wrote a grant to go, like a very small grant to get a couple of spectrophotometers that I use for this, and I use for a couple of other things. So going to the workshop really helped me ramp up that grant and get it like funding ready, because they saw that I was doing something maybe new with it. But in this one, I did, I hope at a little bit higher level. I'm not sure that I did, because what Jenny looks like she's doing in 8th grade looks pretty amazing. But this was a real opportunity for me to integrate just a review of factor label and dimensional analysis. You can see in the pre-lab questions, and this they're doing in a laboratory notebook, about let's get an idea of how big this is compared to that. So kind of a powers of 10 type of thing. And a couple of biological examples in there. So in this one, they were making some silver nanoparticles, and we were using the specs to kind of analyze the spectrum from that. And I have in the folder that I shared with Maria, I have both like the JChem Ed article that probably somebody gave it to me, so I hate to say I found it, but probably I found it at the workshop when somebody put it in my hand during the summertime, but I guess I found it there, so there you go. And then I also included like my adaptation of that there for whatever it's worth. And besides that idea of like bulk versus surface, for me, this one was really to kind of reinforce that idea of scale and, you know, kind of powers of 10 in addition to that bulk versus surface. So those are the things that I've integrated. It's been much less of a central shift in my curriculum than I think what Jenny Thomas did. It's been more like activities where I'm kind of like pulling from my regular curriculum into these activities rather than putting it the other way. But I just wanted to encourage like anybody who's out there and wants to try something new, you know, you can start small, no pun intended, and start with something that's really easy to put together and then move on from there. So that's about what I have.
So good. Thank you so much, Suzanne. I have a quick question for you. This is Marielle.
Yes.
I completely agree. Start small, and like those kits that come up from like Flynn. I've been using the Ruby Red Colloidal Gold for years. And here's the tip. And so I am not a chemistry teacher. I am a physics teacher. So what do I know about water? Water is water, right? No, you have to use distilled water. If you don't use distilled water in the mixing of it, then it never forms. They never form because we have too many And all of the chemistry teachers are like, of course, right? But like, there's a tip for everybody who's not a chemistry teacher who wants to do this. And the kids go nuts when it
Yes.
turns red. They love it. They videotape it. They think it's like magic. It's so
They
great.
put
They
it on
love
their
it.
story, yes. But I
Mhm.
did not, so I always use the distilled water because I am a chemistry teacher,
Right.
and we actually have a still in my prep room. And I would also mention that it is past 5 o'clock where I am, so I'm just saying. But you know, I did not know that really if you don't use distilled water, it won't work. But I might actually, with a little tiny bit, I might actually try that just to point out that's like an example of how all those ions are in tap water compared to distilled water.
Well, also, and well, there's an extension on the lab too, where you can save it because it's fairly stable. The
Mhm.
red that we make, I think it's like 40 nanometers or 20 nanometers,
Yeah.
but it's quite stable where it is. If you add salt to it, it just precipitates out because you get rid of all of those. I think it's the negative ions that are
Yeah.
the corona around the
Mhm.
nanoparticles. But what you can do is what I've read a couple times and I've done. Kids can bring in electrolyte solutions like Gatorade and Powerade, and they bring them in and then they add them in a controlled way to like little. So you take the red that you made in quantity and you
Right.
put it into different test tubes. And then in the test tubes, they use droppers and they add in all these different electrolytes, and you see which one is the best. And hands down, coconut water.
Ooh.
Which is an interesting takeaway, right? So the
Yes.
kids are like, what? Because nobody would drink salt water to rehydrate yourself, right? That's not healthy. But like if you go through all the healthy options, it was kind of an eye-opener. So
That
but
is
then
very interesting.
I'm wondering, do you have any tips about the silver? Because I've never done that one. I have it, but I've never
So
done
it
it.
is a little finicky. It's really finicky. Okay. So if you, again, start not only small, but start with a sure thing. Okay. So like the silver one is much more finicky, but I don't regret having it because that's how I got my extra spectrophotometers. Like, you know, so it was worth it. Right. But I don't really have any tips for that except for like everything needs to be so clean. You know, like the glassware and stuff that you're using, I actually rinse that out with distilled water myself before you know, before the lab, like the particular pieces that I'm going to have out, and like the stir bars. So I would rinse those off with distilled water, you know, beforehand. And if I may, like that is something, if I don't know if it's appropriate for me to suggest this or whatever, but I'm going to do it if it's okay. So if you're running a workshop, like if you're a university or a commercial partner and you're running a workshop, I think it is really, really important to go through how to use one of these things from start to finish, including any sort of like prep that you might need to do. If I could make a suggestion for the university people who might be running workshops. And I haven't been watching the chat too much, but Maria, it would be fine that folder that I shared, it is open to whoever, like it's open for the link. So it would be fine to share that with in whatever format you want. And I think everything in there is, the sources are very clear.
Yes, and thank you about that. I
Okay.
actually was answering questions about it. There's a Google Doc with resources that we have been compiling after every session. Under October 4th, you'll see the link for the resources that Jenny shared and the ones that Suzanne shared. And you don't have to save the link right now. We'll send it over email to everyone. And someone also asked if all the links that are being shared are going to be accessible. I'm adding them to that Google Doc as well.
Yes, Maria is amazing at keeping track of everything that's going on. This was so helpful. I'm so encouraged to like hear a teacher, even another teacher saying, yes, like start small, try something out, because it's literally so much fun. The kids love it. They find it so interesting. And I'll tell you, I've got so much of the gold nanoparticle stuff. I have it in these like old fashioned looking containers on my desk, and all of my physics kids, what's that? Why is that? What is it? And like, they can't believe it's gold because it's red. So yeah, it's a great activity. Thank you for sharing. Thank you so much for sharing. This is great.
Any questions or any resources they want to share? I know we have some representatives from the different nano centers. I don't want to put you guys in the spot, but I'll just put a plug for you, all of you. A lot of them run RETs over the summer. These are paid opportunities for you to learn about nanotechnology and how to incorporate it into your classroom. There's different flavors and formats to it. I'll let them speak up if they want to. I think applications are not open yet because it's too early, but just keep it in mind, keep it in your radar. I think Jenny did one of those programs as well, and Suzanne did as well, so they can tell you a little bit more about it.
Yeah, maybe I'd like to say something. Our symposium, annual education symposium, is coming soon, and I will, re-invite some of the speakers from last year, but I will invite everyone to attend it. It will be on Saturday, November 11th, and I will send you all the information, Daniela, Maria, and the network here. Also, we have an REU and RET program every year. We start recruiting in November. So if you're interested, that's good. We also do a Nanotechnology Summer Institute like Daniela does at Stanford. We have, I think I've trained about 67 people in the last 3 years. So that is ongoing. So if you want to be a part of it, we cover some of the same topic that we discussed. There is a self-assembly. We talk about light extensively. So Jenny, there's a lot of commonality in there. Also, just let you know, today was the Nobel Prize, the announcement about the Nobel Prize and quantum dots. We have actually, with our collaboration with UCSD Merced, developed a quantum dot kit. So if you're interested, we can loan it to you as long as you return it. Just let me know. I would be glad to send you the kit for your classes.
I bought a 4 vial quantum dot set that I keep in my refrigerator at work. It's wonderful. It's tiny, but it was affordable. It was like
ours are silicon quantum dots. What we do is we make very teeny holes, pores in the silicon, and we can show that they fluoresce. Also, what is cool is we have this exercise where we show that they are super hydrophobic, right? So you compare silicon and quantum dots, and you can see that when you deposit a drop on the silicon nano quantum dot, it remains pretty much, semi-sphere. When you put it on the regular silicon, it just flattened, right? It's just flat on it. It's very hydrophobic. So that's another interesting aspect. And we cover a little bit the quantum nanopores have, the quantum does have this hierarchical structure, right? So small structure on top of your even smaller structures. And that mimics the lotus leaf. That's why it confers this super hydrophobicity. So you can cover both, both lessons at the same time.
That's amazing that you do that, Yves. That's fantastic. Are they? I just have to ask. Like, it's selenium, right? Is it? I've never had them outside of a vial.
A quantum dot?
Yeah.
Yeah, I can show you one actually.
No,
And while Yves is grabbing that, I just want to also point out that Yves is also part of a network called the RAIN network, where you can actually
the
schedule
slide
your class.
on the right or on the left. I'm not sure where you are. It's regular silicone. On the other hand, it's the same type of material, same piece of silicone, but has been,
coated.
Worked on to make these nanopores. So if you shoot UV light on it, see now now if I irradiate it, right, I mean, it's
Yeah.
oops, pretty much white. If
Mhm.
you do UV light, I hope you'll see it. It's now kind of orange. You know, it's reflecting a little bit orange. Maybe tough to see, but in your class, you'll see it very easy. And the kids are
Nice.
always impressed. Of course, they go from white to orange, and they wonder what's happening, right? It's fluorescence. And what is cool with this is that, you know, very often you process light through the material. In this case, the material emits lights, right? It doesn't process light, it just emits light.
That's
And
awesome.
Eve, as you were grabbing the materials, I was just pointing out that you also are part of the RAIN network and that they could have an opportunity to have their students remotely run a scanning electron microscope and look at different samples.
Yes, we do that too. You do that too, Daniela, right? With your new microscope, or?
No, I'm not part of
Yeah.
the RAIN, but we just got our tabletop SEM, but we're not doing remote right now. We're just
Okay.
trying to first do it on campus.
Well, you know, you're all invited to communicate with me and arrange for a remote SEM session. I would be more than glad to do that.
Yes, absolutely.
If
And
you
I
guys are,
also-
go ahead.
Oh, sorry, Maria. I also was just going to mention that I'm a product of an RET. I think they're amazing. If you have the time to commit in the summer, it's a wonderful program. It will be life-changing for your classroom and for you as a professional. But if you don't have the time to commit to like an 8-week summer program, the program that we have at Stanford and that Eves has at San Diego really is sort of a stepping stone where you're only going to be there for a week. Mine is specifically for middle school teachers, and we also have a virtual program. And I'll put our website in the chat and you could check that out. But Eves runs a high school program as well as a middle school program. So there's a lot of options if you're interested in getting a little bit, you know, deeper into nano.
A lot of options in California.
Yeah, yeah.
We just completed a 3-year RET at Stevens Institute of Technology over in New Jersey. And this spring coming up, we're going to be doing a nanoscience workshop for middle and high school teachers. So if you're on the East Coast and you want to, and you can get up to Hoboken, we'd love to see you there. And so that'll all be part of the information that we continue to share on this at this forum.
Yes, and one more thing. It's not just 2 states. There's different RETs that's focused on nanotechnology throughout. There's one in Georgia, there's one in North Carolina, there's one in Kentucky. So there's might be something closer to you, and we'll notify everyone once those dates and availability is being published. And one more thing I wanted to mention, Eve and Daniela were talking about the RAIN network. We actually had a session about how the RAIN network works in this forum last year, and in the resource package, there's links to that and the video recording, just so you see how easy it is really to control an SEM over Zoom. Really, that's how you're doing it. It's very straightforward, and it's a very cool resource to use, and it's completely free. Okay, with that, one more thing, and then I'm gonna stop. There's I think that a lot of students get really excited with the wow factor, and as many of you know, Mark Rover is one of the most famous engineers in YouTube right now, and he happened to put a video about nanotechnology last week, and he was trying to do the world's smallest Nerf gun, and he went down to nanometers using carbon nanotubes, but then he went even smaller using DNA origami. It's a very cool video. It's a great way to introduce students to nano in a fun, dynamic way. And I also included that video in the link of resources. And with that, is there any other comments or questions before we adjourn?
Well, it's great today. Thank you for the presenters, and thank you, Maria and Daniela.
And Marielle, thank you, everyone. Thank you, Jenny. Thank you, Suzanne. And thank you all for being here. Hope to see you in November.
Thank you, everyone. A pleasure. Take care.